Welcome to Architectural Insights with KING-KAMBUF. This is our daily interdisciplinary mentorship brief for Monday, December 15th, 2025.
Good morning.
This brief, as always, is brought to you by the services of KING-KAMBUF PS Architecture. We're here to give you that daily edge with a mentorship digest.
And for today's deep dive, we are really training you to look beyond the finish line. We're going past the completion date, past the ribbon-cutting ceremony.
But we're past it.
And into the messy, unpredictable reality of a built environment after everyone goes home.
Exactly. Our mission today is laser-focused. We're talking about that phase where the drawings are all filed away, the construction dust has settled, but the real work, the real architectural and engineering responsibility is, in a way, just beginning. We are squarely focused on ownership, control, and post-construction power dynamics. And for you, listening, you need to master this transition.
That's right. Because the conventional wisdom, what you're taught, is to focus on design and delivery. Get it built, get it signed off.
Get the permit, move on.
Right. But elite practice, that requires you to think beyond that. Beyond the immediate delivery, beyond the occupancy permit. True mastery means you have to focus on the long game.
Which is?
Governance, operations, and, this is the crucial part, how to maintain the intent of your architectural authority long after you've handed over the keys.
So this idea that you, as the designer, you build this high-performance system and then you just move on to the next project.
The broken model.
That paradigm just doesn't support high-level practice anymore, does it? Especially not in public work or complex institutional projects.
It absolutely doesn't, and we've seen this, and all the sources we're pulling from today confirm it. There are two critical shifts happening globally that fundamentally redefine your professional mandate.
Okay, what's the first one?
First, the idea that the architect's responsibility, and frankly their influence, it shouldn't, and I'd argue ethically cannot, end at occupancy. Your professional liability and your ethical commitment to the project's promised performance, it continues.
And the second shift?
The second shift is the recognition that true longevity in the built environment. It's about designing buildings that survive more than just time or weather or, a hurricane.
Right.
They must survive the challenges we introduce ourselves. I'm talking about fractured governance and unpredictable, often counterproductive human behavior.
So we're moving from designing for this perfect, static, ideal condition that exists on paper.
A fiction.
To designing for a dynamic reality, for uncertainty, and let's be honest, for a certain amount of organizational chaos.
Precisely. And that's the intellectual leap we're forcing today. Understanding these concepts, treating failure as a core design input and seeing building management as a system to be designed itself, that is what ultimately separates you from just being a competent practitioner.
And the stakes here are huge. We're talking long-term performance, financial sustainability for the client, and at the end of the day, your own professional accountability. Okay, let's unpack this. This seismic shift in authority. I want to start with what the sources are calling the architect's diminished role post-occupancy.
The authority gap.
The authority gap, exactly. Looking at the industry pulse data, the global trend is, well, it's pretty clear and it's challenging. Architects are increasingly being excluded from the operational and maintenance decisions that inevitably reshape their buildings.
And it happens fast.
It's especially noticeable and really problematic within that crucial first 5 years after substantial completion.
That 5-year window is the crucible for the building. It really is. It's when the entire system is truly tested by its operators for the first time. It's the moment where a facility either stabilizes into its intended performance, hitting those promised sustainability metrics, the cost savings, or, and this is far more common, it degrades rapidly, all due to 1,000 small, often undocumented ad hoc changes made by the people on the ground.
And the owners, especially public sector clients with tight budgets, they're seeing the massive financial fiat from this degradation, aren't they?
Oh, absolutely. The sources are clear that owners are finally recognizing that those early operational changes, the little tweaks to the BAS, reprogramming set bed temperatures, shutting off smart features because the staff finds them annoying.
Right.
All of that often completely undermines the original performance targets that were promised, that were established back in the design phase.
Think about the contracts, the promises made in the initial RFP. You have a building designed, modeled, financed for, let's say, a 40% reduction in energy use compared to the code baseline.
A huge capital investment is made based on that promise.
Exactly. But then, 18, maybe 24 months in, the facilities management team disables the heat recovery system because it sometimes freezes in the winter, or they start running the perimeter VAV boxes manually because the sensors are a bit slow.
And just
So
like
no,
this.
suddenly that promised efficiency drops to 15% or less. That massive capital investment in high-performance features has just completely failed its fiduciary duty.
And the architect, who is morally, if not legally, tied to that performance promise, they're often completely cut out of the decision-making loop that caused the failure in the first place.
Which brings us to the fundamental challenge that the sources pose for you, for the listener. How can you, as an architect, contractually and maybe more interestingly, spatially retain influence after you hand over the keys?
It's a multi-pronged approach. Looking at the post-occupancy governance review and the Global Facilities Decision-Making Forum, we see a couple of paths. Contractually, retaining influence means you have to negotiate for long-term monitoring, for operational consulting services. Maybe it's structured as a performance retainer.
Having some skin in the game post-occupancy.
Right. But spatially, which I think is a harder and more elegant challenge, it means designing the building in a way that actively resists unauthorized or ill-informed modification. You have to make poor performance difficult to achieve.
That idea, that spatial retention of influence, is genuinely fascinating. It means the design itself has to act as a constraint on bad behavior. It's not enough to just hand over a thick operational manual that no one will read. The building itself has to guide the user. It's not about a confusing control panel. It's designing the system so the easiest, most convenient path for the operator is also the path that maintains the building's highest performance.
The path of least resistance has to be the path of maximum efficiency.
Which leads us right into this major source of conflict the data points to. Facilities management as the new design battlefield.
It is a battlefield. The reality, supported by all the data we have, is that the facilities managers, the FMs, they are the ones who hold the ultimate control over the building's daily performance. And they routinely override, or let's say dumb down, the design intent.
And my immediate reaction, and I think a lot of people's, is to blame the FM. But you're suggesting it's rarely malicious. It's just practicality, right?
It's almost universally rooted in operational pragmatism. I mean, the sources point to very understandable root causes. This overriding is often driven by severe and often unexpected staffing limitations.
So they might have two people managing a complex system that was designed for a team of 4.
Precisely. Or it's driven by budget constraints. It's politically easier to avoid replacing an expensive custom filter or a specialized sensor than it is to justify the cost. Or, and this is a big one, it's just simple, pragmatic risk aversion.
Risk aversion is a powerful motivator. If a complex system might occasionally throw an error code or cause a minor complaint from a tenant, the FM's fastest path to a quiet afternoon is to just set the system to manual and forget about the high-level performance features.
Exactly. Take a highly efficient variable refrigerant flow system, a VRF system. They're amazing when they're running correctly, but they are extremely sensitive. They require specific, expert calibration and monitoring.
Okay.
Now, if the operations team lacks that specific expertise, they might just revert to running simpler, less efficient chilled water loops because that's what they're familiar with. It's easier to troubleshoot, and it's less likely to generate a middle-of-the-night alarm call.
So if the design demands specialized, deep knowledge, or if it makes routine maintenance harder, the FM is almost guaranteed to simplify the process.
Even if that simplification completely tanks the high-level performance metrics the design was supposed to achieve.
The ultimate outcome, then, is a building that's optimized for maintenance convenience and minimal operational risk, rather than the high-level metrics, energy, air quality, user comfort that the design team and the public were aiming for.
We are seeing these incredibly robust systems being operated in their lowest common denominator state. It effectively neutralizes the entire design investment.
This brings us to what I think is the ultimate design test, straight from the International Facilities Futures Report and the Building Operations Intelligence Lab. And that test is, design a building that cannot be easily misoperated.
That is a fundamentally different and much, much tougher design brief than just designing a highly performing building under ideal conditions.
It forces you to build operational resilience into the physical structure itself.
It requires a design that actively anticipates and compensates for the inevitable staffing cuts, knowledge loss, operator apathy. It means the building has to be smart enough to self-regulate complex sequences, but simple enough that the overrides are difficult or obvious or physically impossible without some serious effort.
Can we brainstorm a concrete example for the listener here? What does a self-defending system actually look like in practice?
Absolutely. Let's think about an HVAC equipment room. Instead of just putting a complex digital control panel on the wall for 3 redundant pumps,
The kind with 100
right?
menus.
Instead, you might use physical, color-coded piping and valves that clearly illustrate the necessary flow and the redundancy sequence. Maybe you physically interlock the high-performance settings with a system that only a maintenance supervisor has the key for. This ensures the default, easily accessible settings are still highly efficient, just not peak optimized.
So the physical layout itself discourages the wrong workflow.
It makes the system self-documenting, which is critical.
Let's shift gears slightly. Let's get into the contractual side of this transfer of power. We need to nail down contractual control and liability. When does this critical shift in control officially happen?
Okay, this is where we need to look at the error study block, specifically question Q1. Why must you, as an architect, understand the difference between substantial completion versus final completion? This is not just legal jargon.
Not all.
These terms define crucial seismic shifts in liability, in control, and importantly, in payment structures. And it's the beginning of the warranty clock.
Substantial completion is the pivotal moment. It means the building is sufficiently complete for the owner to occupy it or use it for its intended purpose. It's the trigger for the release of retainage, the start of major fee percentages for the design team.
And critically, it's the moment the clock starts ticking on all the major contractor and supplier warranties.
And that warranty clock is massive.
The shift in liability happens so fast after that point. We need to contract the punch list, which covers the minor, cosmetic, or incomplete items you note before substantial completion things. Things like chipped paint, missing doorstop.
Minor stuff.
With latent defects, these are the big ones. Structural or system failures that are not readily observable until after occupancy, sometimes years later. Substantial completion transfers control of the site from the contractor and the project team to the owner's operational team.
So if the owner takes occupancy at substantial completion and an employee immediately misuses an advanced system and causes damage, that liability discussion instantly becomes a lot murkier than if it happened during construction.
Precisely. The contractor is still on the hook for punch list items, but the control over the facility's operation has shifted. Substantial completion is the contractual moment when your design stops being a static product under creation and starts being a dynamic asset under management.
Which is why high-level firms are now negotiating contractual language for post-substantial completion services.
You have to. Not just for punch list management, but for operational monitoring, for training refreshers, for performance audits. You have to do it to ensure you retain a seat at the table.
All right, moving on. Especially when we're dealing with public funds, with taxpayer assets, we run into the political and organizational structure that can directly challenge a building's performance. We're talking about the public asset ownership paradox.
This is maybe the greatest governance challenge in the public sector. Clarity is so often sacrificed for political accommodation or just bureaucratic necessity. We see extreme fragmentation of authority all the time.
Give us an example.
A single public building, say a state operations center or a municipal stadium, it might be owned by a state building commission, operated by the city parks department, and maintained by a completely different third-party facilities management contractor.
I can already hear the finger pointing. When the energy bill is 20% over budget, the owner blames the operator blames the maintenance contractor for using cheap parts, and the contractor blames the architect for a design that was too complex.
That's the failure cycle in a nutshell. The sources, including the Public Asset Governance Quarterly and the Infrastructure Stewardship Institute, they highlight that this fragmented authority inevitably creates significant performance gaps and, most critically, massive accountability failures.
Because no one is in charge of the whole system.
Exactly. When budget decisions, operational authority, and maintenance execution are split between 3 or 4 different entities, no single entity has true end-to-end responsibility for the health of the whole system.
The person who decides to cut the utility budget isn't the person who has to monitor the utilities.
Right.
And the person monitoring isn't the person who has to change the specialized filters in the mechanical room. The silo structure guarantees operational gaps.
So the design solution, therefore, it has to be highly integrated. It has to be fundamentally resilient to that kind of administrative fracture. We have to design spatial systems that can function effectively despite a fractured governance model.
How do you even do that?
It means making the operational requirements spatially obvious. So obvious that disparate, non-communicating teams can understand the necessary functioning of the building without needing complex interdepartmental agreements.
That idea that a poor political structure shouldn't necessitate a poorly performing building, that is a powerful mandate for the designer. It's demanding that architecture be almost politically neutral in its function.
It does.
Yeah.
Which brings us to the critical role of human factors and the human and operational cost. And I want to focus on the loss of institutional knowledge.
Q5 in the source material asks a very practical, real-world question. Why do buildings fail faster after staff turnover?
The answer is so simple, yet it's devastating. It's the rapid loss of operational knowledge. Institutional memory just walks out the door.
The one person who knew how the complex chiller controls were commissioned, who understood the strange sequencing logic, or who had the cell number for the system vendor. They retire or take another job.
And suddenly, the remaining staff, who might be perfectly competent but just unfamiliar with that one system, they revert it to a manual, inefficient, but safe state, just to avoid system faults and keep the lights on.
This is where we have to embrace an expanded architectural role. You're saying architecture itself must function as a form of institutional memory.
It has to. The design must encode operational requirements into the physical form and layout. If a specialized air handler unit requires quarterly internal inspection because of its unique filtration sequence, then its location, the dedicated maintenance access, even the warning signage, it all needs to be integrated into the physical form.
Making the operational requirement undeniable.
Undeniable, regardless of who holds the key that day or who attended the training session 5 years ago.
This connects directly to resisting operator error, which is Q6. The sources constantly remind us that human factors dominate failure rates. So why must engineers design systems that actively resist human error?
Because systems are so often designed to perfection, assuming perfect operation and perfect maintenance. And that is a fallacy of the highest order. It never happens.
We have to move past that ideal.
We do. We need to explore the critical difference between fail-safe and foolproof design concepts. The sources highlight this as a key distinction.
Okay, break that down. Fail-safe versus foolproof.
A fail-safe system that might default to a state of safety? Think of a commercial elevator. If it loses primary power or detects a fire, it stops dead and locks down completely. It minimizes the immediate hazard.
But a foolproof design goes a step further. It proactively prevents the unsafe condition from ever being introduced in the first place.
Exactly. A foolproof system is one where you cannot accidentally start a major piece of machinery without first checking a physical interlock, or where a critical valve can only be turned in one direction because the pipe geometry physically prevents the wrong action.
So it makes it difficult or impossible for the operator to introduce an unsafe condition, maybe through mechanical constraints or really clear, single-use, non-ambiguous interfaces.
Recognizing that human factors are always the dominant variable in long-term failure. That's the key to designing for real-world resilience.
And when a system failure does happen, or when performance just tanks, the spotlight shifts instantly to legal and professional accountability. This all hinges on the role of documentation in accountability. Signal C from the sources makes this painfully clear for every professional involved in an asset's lifecycle.
Recent high-profile building system failures. Think about catastrophic parking structure collapses, facade failures, utility tunnel breaches. They've created a dramatic legal and ethical shift in professional liability.
How so?
The focus used to be primarily on who designed it or who built it incorrectly during the construction phase. Now the overwhelming legal focus is increasingly on who ignored the warning signs during the operational phase.
Wow. That is a tectonic shift. It means a perfect design can still be the subject of a massive lawsuit if the operational team fail to heed its built-in warnings.
It does. Maintenance logs, sensor monitoring data from the BAS, documented repair schedules, that's now central evidence in professional liability cases. If your design provided clear warnings, say, through strain gauges in a structural component or persistent high-pressure alerts in a mechanical loop, and the operational entity failed to act on them,
the liability shifts.
it shifts decisively toward the operational entity and away from you, the original designer or builder.
The key insight here is stark, and really it's non-negotiable for anyone managing assets. Failure without documentation is negligence. If you're managing a public asset, every maintenance action, every override, every inspection, every performance warning, it has to be meticulously logged.
Or you risk professional and legal exposure in the aftermath of an incident.
And this need for clarity, it extends to the decision-making process itself, right? Especially in complex public projects. Q4 stresses the absolute importance of authority matrices.
Yes. These matrices formally define who has the power to make which decision. Ambiguity in decision rights like who can approve a major system override or who can authorize a tenant-mandated structural modification, that ambiguity leads directly to unsafe or inefficient changes.
An authority matrix is basically a roadmap of command and control for the building. Why is its absence so dangerous?
Because without one, critical safety or performance decisions are often made by default, by the person who just happens to be available, or by the lowest common denominator staff member who needs to solve an immediate problem right
Well,
now.
it's reactive, not strategic.
Completely. It avoids the chaos of competing departments. It ensures that when the facilities manager decides to disable that automated shading system we talked about earlier, they first have to get approval from the sustainability officer, the legal department, and maybe the building owner. All of them have to sign off against their documented KPIs. Clear documentation of decision rights is mandatory for complex assets.
Okay, let's shift our perspective entirely now. Let's move away from avoidance and towards acceptance. We're now going to treat failure not as something to be ignored or prevented at all costs, but as an input, something we have to design around and critically engineer for. This is graceful failure, the new engineering ethic.
Signal A introduces a truly progressive and, I think, ethically robust concept. Global infrastructure agencies are now adopting graceful failure design standards. This moves us away from that unrealistic expectation of perfection and maximum strength in all scenarios.
So we're accepting the inevitability of systems failure. But we're demanding that when they fail safely, predictably, and in a way that minimizes catastrophic consequences. This sounds like an engineering philosophy borrowed straight from aerospace-controlled destruction.
That is precisely the core concept. It's about engineering the failure pathway itself. Structural and MEP systems are now increasingly being evaluated based on their failure sequencing, not just their maximum ultimate strength.
Give me an example of that.
Okay, if a pipe bursts in a data center, the question isn't just, did the pipe burst? It's, where does the water go? Is it diverted away from critical electrical components? If a column fails due to an explosion, does the load redistribute safely to adjacent members? Or does it trigger a catastrophic cascading collapse?
So instead of only asking, can this column hold 100 tons, we're now asking, if this column is suddenly reduced to zero capacity, how long does the rest of the structure hold, and how does it signal its distress?
Exactly. The key insight from the Global Infrastructure Systems Review is that resilience shouldn't be understood as resistance, that futile effort of preventing failure entirely. It should be understood as controlled collapse, ensuring continuity of essential functions, and enabling swift recovery. We are explicitly designing for the aftermath, assuming the event, whether it's a fire, a seismic event, or an operational error, will occur.
And this philosophy, it expands so quickly beyond a single structure and into the realm of the city itself when we start to consider managing system interdependence.
It has to. The modern urban environment is not a collection of isolated assets. It's a giant, fragile network.
And Signal B confirms this, right? Urban planning is moving beyond just mapping isolated hazards like a localized flood.
And into mapping cascading failures. We have to model these complex scenarios where, for example, a major electrical substation failure triggers a failure in the municipal water pumping system, which then triggers a healthcare facility failure because they lose water pressure and fire suppression, which then leads to a governance failure because the emergency command centers can't communicate without power.
That requires architects and urban planners to collaborate much earlier with systems engineers, with utility managers, with emergency managers.
The layout of the city, the redundancy built into its essential infrastructure, which is often just a collection of individual buildings, that determines the severity of the crisis.
The key insight here is that the urban form itself dictates how failure spreads, or, critically, how it stops.
Absolutely. If all your essential services, backup, fuel storage, emergency transit hubs, are all concentrated in one low-lying, flood-prone geographic zone, then failure is going to be more rapid and total.
But if they're geographically distributed and networked via diverse load paths,
then the system has inherent resilience, even if individual components fail.
This brings us right back to Q1 in the AR module. Why must critical buildings analyze single-point failure?
The answer is that the loss of one single, seemingly minor component, like a specific switchgear in a hospital basement or a single chilled water pump in a data center, can disable an entire massive system. It doesn't matter how much redundancy you have elsewhere.
The ARE test system interdependence for a reason.
It does. You have to be able to identify the choke points. If your facility relies on two parallel utility feeds, but both of those feeds run through the same 5-foot section of a single tunnel, you don't have resilience.
You have zero resilience.
That one section of tunnel is your single point of failure. Designing for resilience means identifying those points and engineering around them, ensuring spatial separation and independent operation.
And as we look for those choke points and engineer for independence, we naturally start thinking about redundancy. But this is where it gets really interesting. Let's explore the paradox of redundancy.
Q2 poses this incredibly counterintuitive finding that redundant systems can sometimes increase the risk of failure.
The knee-jerk logical assumption is that two backups are always better than one. It just seems obvious.
It seems obvious.
But practically, why isn't that true? Why does complexity actively fight against reliability?
The cause, overwhelmingly, is that redundancy introduces coordination errors, training errors, and maintenance errors. Think about a standard, heavily redundant fire suppression pump system. You've got pump A, pump B, and a diesel backup pump C.
Okay.
In a perfect world, they are all tested and maintained equally. In reality, operators might only run pump A regularly, relying on B and C as dormant backups. They forget to service B and C, or the software that coordinates their switching sequence during an emergency gets corrupted during a routine IT update nobody told them about.
So when the emergency hits, pump A fails due to expected wear and tear.
And pump B is seized up from disuse because the maintenance checklist was missed a few times. Pump C might run, but the corrupted software sends it the wrong pressure target. The system failed because the redundancy layer introduced too much maintenance and operational complexity for the staff to manage consistently.
Wow. The lesson is clear and vital for anyone listening. Redundancy without clarity is fragility.
It is. Any redundant system must have an extremely clear, physically legible, and easily testable protocol for maintenance, transition, and operation. If the complexity introduced by the backup system outweighs the operational capacity of your staff, you haven't bought resilience, you've just created more opportunities for human error.
Speaking of structural integrity, let's nail down structural robustness and code requirements, where this concept of controlled failure becomes physically mandatory.
Right, we're talking about progressive collapse. This is addressing Q3 and the code byte section. This is a crucial principle mandated for specific occupancies that says a local failure, the loss of one load-bearing column due to an explosion, a vehicle impact, a localized fire, that failure must not trigger a disproportionate amount of damage leading to a total building collapse.
Structural continuity must be intentional. It has to be engineered into the load path.
This requires a fundamentally different mindset from just standard design. We're not just designing the column to hold its maximum static load, we're designing the surrounding beams, the connections, the slabs to be strong enough to bridge the gap and carry the load to adjacent columns if that original column just vanishes.
We call that designing alternative load paths.
Exactly. The sources note that the IBC references progressive collapse mitigation for certain high-risk occupancies. It mandates that load paths must remain after localized damage. This is done through concepts like tie forces, internal structural connections that prevent individual floor slabs from peeling off the frame, ensuring the structure remains one continuous, coherent element, even when it's been severely compromised.
It just shows that designing for failure scenarios is deeply ingrained in the current code intent.
It is.
Finally, let's consider the aftermath of an event. Q6 asks, why design for inspection after a failure? This sounds like an obscure point, but its practical implications are enormous.
Because post-event assessment governs reoccupancy and the speed of recovery. If a building is hit by a localized event, a small earthquake, a heavy fire, you need engineers and inspectors to get in there and rapidly determine its safety.
And if they can't?
If critical structural connections or utility shutoffs or seismic isolation joints are hidden behind custom finishes, or they're inaccessible in some tiny crawl space, or destroyed in a way that prevents quick visual or instrumental assessment, the entire building may remain condemned or closed indefinitely.
And that closure, it just hammers the owner's bottom line and the public's ability to use the facility.
Absolutely. The lesson is simple, but it's vital. Access is a life safety feature, and inspection access is a feature of resilience. Designing in clear, accessible pathways, ensuring that critical connections are observable post-event, it speeds recovery and ensures continuity of operations. You are designing not just for the building's survival, but for its rapid return to service.
Okay, we have spent a lot of time on theory and contracts. Now it's time for our daily drill. We need to take this theory on failure and governance and apply it in a practical scenario. building up that professional reasoning you need under pressure. We call this the self-defending building prompt.
This exercise is crucial because it moves you beyond just relying on ideal contracts, and it starts demanding real design intelligence. The prompt asks you to design a public building that maintains its performance, safety, and functionality, even when it is inevitably, eventually, misoperated.
And we have constraints drawn directly from the sources that reflect real-world operational reality. You have to assume reduced staffing and minimal training. This is the worst-case operational scenario.
No ideal conditions.
None. You cannot rely on complex controls or esoteric digital management systems. And crucially, the intended performance must be legible through the form and layout itself.
So, if the building relies on a specific thermal chimney effect for cooling, the geometry and location of the operable windows and vents, they need to be so explicit that an operator would instantly understand the physics of how it works,
They would have to actively sabotage the system to make it fail.
rather than just passively neglecting a confusing digital control panel.
I think this exercise connects directly to that massive upcoming opportunity we've been tracking, the new statewide public asset operations and training campus RFP. Instead of designing just another static building, the suggested angle for this project is brilliant. Propose the campus itself as a living operational manual.
A living operational manual, I love that phrasing. It means the spaces themselves teach operations through daily use, not through a 500-page binder that sits on a shelf.
Exactly. Imagine a facilities wing where the high-performance building systems, the chilled beams, the hydronic loops, the daylighting controls, they're all exposed and color-coded. The maintenance access pathways are wide and obvious.
The system forces the operator to follow a physical workflow that visually demonstrates the principles of thermal management and energy recovery.
Let's detail that a bit more for a listener who's maybe thinking about attempting this RFP. The living manual concept suggests the building has to be didactic. It has to teach.
It does.
Perhaps the energy performance data is displayed in real time, not just in the facilities office, but in the public lobby, creating social pressure on the operators to maintain efficiency.
Absolutely. And furthermore, the operational pathways must be linear. If you need to shut down the main water line, the path to that valve shouldn't require you to walk through 3 separate, locked departments. The spatial organization itself reduces the administrative friction that leads to poor outcomes. The campus teaches the required standard of care simply by existing.
Okay, now let's put on our professional reasoning caps and walk through 2 specific real-world scenarios. Let's start with operational conflict. This is the classic battle between designer intent and facilities management reality.
Okay, the scenario is a new high-performance civic office building 18 months into occupancy. The issue: the facilities team, they're under intense pressure from tenant complaints about flickering light and confusing changes, and they have unilaterally disabled the automated shading system.
The outcome is quantifiable degradation. Energy use is up 35% because the whole cooling system relies on those shades to reduce solar heat gain. And ironically, glare complaints are now increasing.
Of course.
Because the design intended the automated shades to manage low-angle sun dynamically, and now they are just manually set in static and often wrong positions. The building is operating worse than if it just had standard low-performance glass.
This situation requires a highly structured professional workflow, a clear protocol for intervention. Step 1. You have to analyze the operational changes against the original design assumptions and the contractual performance guarantees. You must establish if this change violated a performance clause.
Step 2. Quantify the performance degradation, which we have, that 35% spike, and you have to translate that into financial terms. How much extra is the city paying per year because of this?
Then, step 3. Meet with the facilities team to identify the true root causes. Was it the user training gap? Was the system programmed to be too aggressive? Was the original vendor unresponsive to service calls? You can't just blame them.
Right, you have to diagnose it.
And then, crucially, step 4. Propose architectural or procedural adjustments that address the human factor. This might mean reprogramming the shades to be less aggressive in their movement, or installing a physical override mechanism that only allows temporary manual control.
And then it defaults back.
It defaults back to the automated high-performance mode every 24 hours. The design has to accommodate the complaint, but protect the performance.
And finally, step 5. You formalize those lessons into updated post-occupancy guidelines. You ensure the authority matrix is updated to prevent a single department from unilaterally disabling a critical system again.
The key lesson here: driven home by this scenario, is a design authority without operational influence is temporary and fragile. Your beautiful, high-performing system lasts only until the first annoyed operator decides to flip the main switch. You have to design to survive the facility manager's practical limits.
Let's shift the pressure entirely now to a construction management crisis, a near-miss structural failure. This tests leadership, technical reasoning, and accountability under maximum duress.
Okay.
The incident. A mid-rise public parking structure, 40% complete. During a major concrete pour, the temporary shoring deflection exceeded predicted tolerances by a significant margin. It triggered warning sensors and alarmed the site staff. No collapse occurred, but the system signaled a profound near-miss risk.
The professional task is immediate, urgent, and involves massive liability. You have to produce a failure response and prevention report for the owner, for the city, for your insurers. This isn't about building the structure anymore. It's about managing the risk and the perception of risk in a public space.
And the required reasoning starts with an immediate diagnosis. Was the issue due to the structural engineer's design assumptions about load capacity, or was it due to the contractor's construction means and methods?
A huge distinction.
Maybe improper shoring installation, insufficient bracing, or pouring the concrete too fast? Those are fundamentally different lines of inquiry with massive legal separation.
And the technical analysis is only the beginning. You have to immediately assess the risk of progressive failure if work continues, considering the loads already placed. The leadership decision is critical. Do we pause construction, mandate a complete redesign of the shoring, or just try to reinforce the existing temporary structure? The delay alone can cause millions in penalties and public outcry.
This is where leadership is forged. You have to decide whether to absorb a massive cost for safety or risk catastrophe by pushing forward. And regardless of the physical decision to pause or reinforce, the final step is crucial. You document the decision for legal and public transparency before you are legally required to.
When failure is narrowly averted, public trust is paramount. The report has to clearly state the cause, the analysis performed, the corrective action taken, and the revised safety factor. The key lesson from this scenario is that leadership is how failure is handled before disaster occurs.
The speed, the clarity, the honesty, and the technical rigor of your response that defines your professional entity in the eyes of the public and the courts.
It's the moment when you earn the title of elite practitioner.
So let's bring this intensive deep dive back to the core insight for you, the listener. True architectural mastery, especially in public works, it requires thinking like a synthetic professional, an architect, engineer, planner, builder, who recognizes that pally shifts decisively after construction.
You can't afford to be an artist who just walks away from the canvas because the paint is dry.
You can't, and this reinforces the necessity of expanding your professional scope, which references Q3. If you want to maintain influence and ensure your design intent survives operational reality, you, as an architect, must actively negotiate for post-occupancy services.
It's not just an ethical safeguard. It's a smart commercial opportunity to manage ongoing risk.
Many cutting-edge firms are now moving toward linking their fee structures to actual building performance, a performance retainer, if you will.
Right. Skin in the game.
You guarantee certain energy usage for 3 years, and your fee is contingent on meeting that target. It ensures you have a reason for early intervention, and it prevents the kind of system degradation we saw in that civic building scenario.
It aligns the financial incentive with the ethical responsibility and, ultimately, with the owner's long-term interest.
Absolutely. So to wrap this up, we have to reinforce the deep connection between professional ethics and contracts. This is precisely why the IRE tests post-occupancy concepts so heavily, as we saw in Q7.
Practice responsibility does not end at occupancy. The design is a living entity, and the professional is ultimately responsible for ensuring its long-term life support.
And so we'll leave you with the final provocative thoughts derived from today's source material. These are questions for you to mull over as you transition into your next professional task. We've established that responsibility doesn't end at substantial completion, but how far must it go? How long should an architect remain responsible and influential?
And perhaps even more critically, for all you system designers and engineers focused on resilience, what component in a critical structure should never fail? And what component must be designed to fail safely? That distinction, when you can clearly articulate it, that's the beginning of a truly resilient and accountable design philosophy.